In this video, we're going to continue our exploration of abstraction via the clock display project. In particular, we're going to focus on the way in which objects interact, particularly through invoking methods on each other. Let's briefly review where we've got so far with the topic of abstraction, particularly in relation to this particular project. So we saw that hours and minutes and seconds behave very similarly as wraparound counters. In other words, they have a value that starts from 0, works its way up towards some limit, and when that limit is reached, then they wrap back around to 0 again and continue to rise and just repeat that process over and over again. So we applied abstraction between those three parts of the time, hours, minutes, and seconds, by creating a generic number display class that is able to count up to some limit and then wrap around to 0. We can create instances of that class with whatever limit we like, and it will then provide the functionality required by items like hours, minutes, and seconds. So that's one way in which we've explored abstraction, finding common details amongst elements of a problem. So the second way in which we've seen abstraction so far is that having built this number display class, we can now proceed to build a clock display class where the clock display implementation needs to have no concern about or no knowledge of the way in which those number display objects are going to provide their functionality. In other words, clock display can make use of that functionality and provide its own functionality without worrying about the low-level details of the number display implementations. And in that way, we've illustrated abstraction by our ability to hide detail. So since all programs are going to consist of multiple objects interacting, how exactly do objects interact? Well, we've seen how to write methods. We've seen that methods provide objects with their behavior, and two objects interact when one object calls a method on another object. It's sometimes useful to give names to the two objects involved in an interaction, and we choose names like client and server to be able to describe the two different roles. So we think of the object as doing the method calling as being a client object, and the object that's responding to the method call as being a server object. So a client object asks a server object to do something for it, and it could be that it asks the server object to carry out some action, or it could be that it asks the server object for some information that the server object has stored within it. In our clock display project, we're going to design a class clock display which makes use of two number display objects in order to fulfill its functionality. And therefore a clock display object will be the client of two separate number display objects. Those two number display objects will provide a service of keeping track of what the current hour, what the current number of minutes is, and providing that information to the clock display object so that the clock display object does not itself have to worry about what those values will be. So a client clock display object will call methods on its two server number display objects. It might be useful to look at this visualization of interaction between the client object, a clock display, and one of its server objects, a number display. In this case, the clock display object is calling a method on the hours number display object. So the numbers display object that's looking after the current count of the hours for the current time. The clock display object will interact with the number display object by calling one of the methods of the number display object. In this particular illustration, the clock display object is calling the getDisplayValue method of the number display object that's storing the hours. So the clock display class defines a field called hours, and we can then call the getDisplayValue on the object referenced by the particular instance variable hours in this case, in order to get a string back, a 2-digit string that stores the current hours value. So the clock display object will be able to use that value in combination with the 2-digit string returned by the other number display object in order to display the full time, hours and minutes. Let's look at the source code now of the clock display class to see how we write the source code to enable elements of one class to access elements of another class. Here's the source code of the clock display class with its 3 fields, and notice that we actually have 2 constructors inside the body of the class that enable 2 different instantiations or 2 different object creations of a clock display object. If we create a clock display object and pass no parameters to its constructor, then by default the clock display will have the time midnight 0000. On the other hand, if we want to set the clock to a specific time at the point that we create it, then we can pass an hour value and a minute value into the clock display, and then those are used from within the constructor in order to initialize the 2 number display objects. This is the method that we really want to focus on, the time tick method. Now what we envisage is that some external timekeeping mechanism will be sending notifications to our clock display object each time it needs to update itself. We're focusing on hours and minutes. If we were monitoring time hours, minutes and seconds, then every second we would expect the clock display object to get a notification. In this case, we're just working with minutes. So every minute, the clock display object is told that another minute has passed, and so it's time now for it to tick, in other words, to move on to the next minute. Now, because the clock display itself is not concerned at all about keeping the count of hours and minutes, it's devolved responsibility to that to its number display objects. When the clock display object is notified of the fact that it needs to tick on, it then needs to pass on that notification to its number display objects. So we see here that the first thing that happens is that the clock display object calls the increment method on the number display object referenced from the minutes instance variable. So this variable here contains a reference to a number display object, and then we invoke the increment method via this call. So we have a variable name followed by a dot followed by a method, and then if the method takes parameters, we'd supply them between the parentheses. In this case, the method takes no parameters. We're simply telling the number display object to increment by 1, and so those parentheses are empty. Now the clock display object's job is not done at that point, because it needs to recognize that if the number display object that has just been asked to increment has wrapped around to 0, then it also needs to increment the hour number display object. So having asked the minutes object to increment, it then asks that object what its current value is. And if the value returned is 0, then the clock display object knows that the minutes have just wrapped around. In other words, 1 more hour has passed. And if 1 more hour has passed, then it must ask the hours number display object to increment likewise. So this is the passing of an hour. So for 59 of the 60 minutes within an hour, this test here will give the value false, and we won't need to increment the hour. But once in every 60 calls to the time tick method, we'll know that that will result in the minutes object wrapping around to 0, and therefore the hours number display object needing to increment itself. So these 3 lines here illustrate very clearly the way in which a clock display object interacts with one or both of its number display objects. The final line of the method is actually what we call an internal method call. Notice that in this case we've simply got method name and then the parentheses that would potentially contain parameters. What we don't have is the name of a variable followed by a dot. What this signifies is that this method is actually being called by the clock display object on itself. So that's what we call an internal method call. And we'll come back to some details on that in a moment. So here this slide captures what we've just described. TimeTick is a method inside the client object, in other words, inside the clock display object. And inside the body of that method are calls to methods of the server object, the number display objects. Minutes.increment, hours.increment, and minutes.getValue. And then finally at the end, an internal or self method call. So what we need to observe about external method calls is that they always have this general form where we invoke a method immediately after a dot character, and to the left of the dot character is the name of an object. Now typically the name of an object will simply be a variable name. In other words, the name of a variable of class type where that variable stores a reference to an object. Now it's very important to appreciate that what comes before the dot is the name of an object and not the name of a class. It would be a mistake to write numberdisplay.increment or numberdisplay.getValue. So even though increment and getValue are methods defined inside the numberdisplay class, what we are interested in is calling increment or getValue on one particular instance of that class, a specific instance of that class. So we're always writing variable dot method name and not class dot method name. It's very important to appreciate that because it's a very common mistake that beginning programmers do, is to write class name dot method name rather than variable dot method name. So a little bit more on internal method calls. When an object is calling a method on itself, it does not need to use variable dot method name because the compiler knows that when those are absent, then it's the object itself that particular method is being called on. Now something worth being aware of is that methods that are only ever meant to be called internally, i.e. by an object on itself, are very often defined as being private rather than public. Pretty well all of the methods we've seen up to this point have been declared as being public, as if they were going to be invoked by other objects, so called as external method calls. But if we know that a particular method is never going to be called by a client object, it's only ever going to be called by the object itself, then we can declare the method as being private rather than public, and we'll often do that. So here's what the update display method looks like inside the clock display class. It's private, it doesn't return anything, it doesn't take any parameters, and all it does is it makes two external method calls to hours and minutes in order to get their two display values, and then it creates a concatenation of those two-digit strings around a colon symbol. So we can see that in action. Let's create a clock display object for a particular time. Let's say the time is 22:46. And then if we bring up the inspector, we will see that here's the display string that is set to 22:46. How has that display string come to be like that as soon as the object is created? Well, if we look back at the constructor that we've just called, we'll see that the hour and the minute came in, two number display objects were created, and then there was an internal method call to the setTime method. What does the setTime method do? it receives those two parameter values, so the hour and the minute that were provided to the constructor, and it asks the hours number display object to set its value to be the hour, the minutes object to set its value to the minute, and then there's a further internal method call to update display. Update display is what we just saw on the slide. So hours.getDisplayValue, external method call, get the 2-digit representation of the hours, concatenate a colon, get the 2-digit value of the minutes, and then concatenate them together, storing them into the display string field of the clock display object. So that's how we end up with 2246 as the string stored in the display string field. So just to add a little bit to our discussion of internal and external method calls, one thing to bear in mind is that if an object of one type were to call a method on an object of the same type but not itself, then that would also count as an external method call and require the use of a variable that's storing a reference to the other object so that the method can be called on that other object. So internal method call means call a method on the calling object, and external means call a method on a different object. Now, just before we finish, there's one thing I'd like to return to, and that is I want to revisit the increment method, because in a previous video I said we could probably simplify quite significantly the body of this increment method. So remember that the purpose of the increment method is to add 1 to the current value stored in a number display object, and then if by incrementing we reach the limit value, then we don't allow value to store that limit. We need to set value back to 0. So that's the wraparound operation. Now, in order to see how we can simplify this, let's look at another operator that exists within the Java programming language. This is the modulo operator. And what we're thinking about here is performing operations between two integer values. Now, typically in programming languages, if we divide one integer value by another, then we typically get a result that's not a fractional result. Integer division usually gives a result in which the remainder is thrown away. So for instance, if we were to divide 17 by 5, the result would be 3 with no fractional part. So the remainder of 2 would simply be thrown away. Now sometimes what we're actually interested in is the remainder rather than the result of the division. And if we're interested in the remainder, then we can use the modulo operator. So that says what value would be left if we were to perform the division between its two operands. So in this case, 17 modulo 5 gives the result of 2, because 2 is left over once we've taken over a whole number of 5s from 17. So let's look at modulo with an extended example. Suppose we look at various values of n modulo 3. 0 modulo 3 is 0, because 0 doesn't divide any whole number of times by 3, and the 0 is left over. Similarly, 1 cannot be divided by 3, so the remainder of 1 when divided by 3 is 1. We also see a similar result for 2. 2 doesn't divide by 3, so again we have remainder 2. However, 3 divided by 3 is 1, and the remainder is 0. Therefore, 3 modulo 3 is 0. And now if you move on to 4, 4 divided by 3 is 1, remainder 1, and so 4 modulo 3, we're only interested in the remainder part, it's 1. And if you look at that right hand column, what you can see is we've got the effect very similar to the wraparound counter idea. In other words, that we start at 0 and we move up to 1 less than the limit. In other words, what we're taking the number modulo. So for modulo 3, it goes 0, 1, 2. If we were taking modulo 5, it would be 0, 1, 2, 3, 4, and then would wrap around back to 0 again. So the effect of the modulo operator is exactly the effect that we want in our wraparound counter that's implemented as the number display class. So in fact, we can rewrite our increment method very simply. We can take the sum of the current value and 1, in other words, we're looking at what would the value 1 greater than the current value be, and if we then apply the modulo operator, modulo limit, and store the result of that back into the value, then we actually get exactly what we want from the increment operator. So value increases towards the limit, but as soon as adding 1 to the value would give us a value that's equal to the limit, then we get a result of 0. And so this method maintains our requirement that value should always have a value in the range 0 to 1 less than the limit. Now it's worth trying out the modulo operator yourself with a few different values on the right hand side of the operator, and on the left hand side to try values that are smaller than the right hand side, values that are larger than the right hand side, and just make sure that you're confident that you understand how this particular implementation of the increment method models exactly the same as the one we saw previously. And then briefly, one final little feature of Java that's worth being aware of. There is a keyword called this, and this acts as a kind of a pseudo variable. So it's something that we write on the left hand side of a dot, and this means this object. In other words, the object in which this piece of code is currently operating. The most common circumstance in which you see this being used is inside the body of a constructor or a method, where defined inside the class there's a field of a particular name, and it so happens that the constructor or the method has a parameter of the same name. Now normally what we would choose to do is to define parameters with distinctive names from other variables that are defined inside the class. But actually it turns out that it's equally common to say I don't really want to have to think of different names for parameters that are going to be used to initialize the values of instance variables. And so the most common circumstance in which you'll see the word this used is inside the body of a constructor, where the constructor is receiving parameters whose names are the same as the fields that those parameters are being used to initialize. And so now we need to be able to distinguish between the parameter of a given name and the field of the same name. And the way that we do that is that whenever we wish to refer to the field, we write this dot and then the field's name. And whenever we want to refer to the parameter, we don't use this dot. And the compiler is able to tell the difference between those two versions of variables that have the same name. So this is not something you necessarily need to start writing for yourself, but as you read code, it's worth being aware that this is very commonly used amongst people who don't really want to have to think about different names for variables that are quite closely related. So in review, what we've seen is that all programs involve interaction between objects, and the way that we represent that in source code is to write external method calls. And it's often useful to be able to talk about client objects and server objects. So the object making a call we call the client object, and that makes use of the services provided by a server object, or the object on which the method is being called. We've also seen that sometimes an object wishes to call a method on itself, and we characterize those as being internal method calls. In that particular case, we don't need the name of a variable. Simply writing the name of the method followed by its parameters is sufficient to cause an invocation of that method on the calling object. And then we've introduced a couple of new features of the language. We've introduced the modulo operator, which is written as a percentage symbol that gives the remainder after integer division between two integers. And we've also seen the this keyword, which is a way of distinguishing between a parameter and a field of the same name. Very commonly seen inside the bodies of constructors, because the parameters are being used to initialize the values of fields when an object is being created.